Want cross-encoder gains without cross-encoder latency? Distill it into a fast reranker. By the end, you will understand how to train a small, fast reranker to imitate a slower cross-encoder, so you get most of the quality at a fraction of the cost. I'm Professor Pi, teaching search and IR with simple Python. Search systems often face a core trade-off. You can score every query and document together with a heavy joint model and get high quality. Or you can use a cheap encoder to pre-compute document vectors and run fast nearest neighbor lookups, but lose some precision. Distilling a cross-encoder into a reranker sits in the middle. You generate supervision from the slow joint model, and you teach a lightweight model to mimic those judgments on ranked candidates. Success looks like near cross-encoder quality while serving in a few milliseconds. At a high level, the idea is simple. Use the cross-encoder as a teacher and produce soft scores for query document pairs. Then, train a click student that uses cheap features like overlap counts and IDF-weighted matches. At query time, the student re-ranks a small candidate set and returns one or a few top documents quickly. Strengths are speed and small memory footprint. Weaknesses are limited expressiveness compared with the teacher. We will build a tiny playground that shows the whole flow on a tiny corpus, so the ideas are concrete before we scale them up. You will see how teacher labels are created, how features are engineered, how a LightGBM LambdaMART student is fit, and how the student re-ranks a new query. This keeps the code light and the concepts clear. Now we bootstrap a minimal dataset to teach from. This snippet builds a tiny IR playground and assigns supervision from a simple cross-encoder proxy. The list QS holds 2 short queries, and DS defines 4 candidate documents. The list Y stores a fractional overlap score for every query document pair, which we treat as the teacher's relevance signal. This overlap ratio mimics a cross-encoder's joint matching intuition while keeping the computation light for the demo. We then average all teacher scores into mu to summarize label density across the grid. The printed mean shows how much positive signal the teacher provides overall, which sets expectations for how hard the student re-ranker's task will be. Next, we extract basic lexical cues the student can use. This snippet turns pairs into features a tree learner can exploit. The counter DF tracks how many documents contain each term, and IDF maps each term to a log-scaled rarity score to capture discriminative value. The variable pairs enumerates all query document combinations in a fixed deterministic order. The feature matrix X contains 2 signals per pair, a hard lexical overlap count and the document length, giving the student minimal structure to learn from. These choices match the distillation goal by being inexpensive yet informative. The printed line confirms we have 2 features for all 8 training pairs, establishing the input shape for ranking. Now, we fit a student model that learns listwise preferences. This snippet uses LightGBM to fit a LambdaMART ranker to the teacher labels. The dataset TR carries X as features, Y as soft relevance, and a group size per query for proper listwise gradients. The call lgb.train with objective lambda rank and a fixed seed builds a small deterministic ensemble. We then score all training pairs with MDL predict to get student preferences. The list cell picks the top document index per query by argmax over each query slice, showing an explicit selection decision. The printed indices reveal which documents the student surfaces, making it easy to compare against the teacher's chosen winners. Next, we try a stronger IDF-aware signal to help the students separate common words from informative terms. This snippet upgrades the feature space with a BM25-like signal, and retrains the LightGBM student. The updated X appends an IDF-weighted sum over query terms found in each document, which helps distinguish informative overlaps from common words. We rebuild the LightGBM dataset TR2 with the new features and refit MDL2 using the same LambdaRank objective for a fair comparison. Predictions P2 are evaluated by top 1 agreement against the teacher per query, aggregated into Act 2 for a clean, interpretable metric. Increasing trees can raise accuracy, but adds latency. Fewer trees do the opposite. The printed top 1 score shows the student tracks the teacher's preferences well. Now simulate deployment by running the trained Reranker on a fresh query. This snippet demonstrates deployment by re-ranking new candidates with the trained LightGBM student. The string QNew is the incoming query, and cand enumerates all documents as a simple candidate set. We compute the same 3 features used in training: overlap count, document length, and IDF-weighted overlap forming F to ensure feature parity. The call MDL2.predict scores each candidate for this query, and top selects the best index via argmax. If you increase features or trees, you may gain quality at some latency cost. Trimming them speeds responses. The printed top document confirms the student can surface a strong result at inference time. Applied to a real system, this same pattern scales. Replace the 2 queries and 4 documents with your query logs and your document corpus. Use a fast approximate nearest neighbor index to generate the initial candidate set. Then re-rank those candidates with the distilled student. The student stays cheap at inference, so you can re-rank many queries per second. Recap. It is distillation where a slow joint scorer teaches a fast re-ranker. Use it when you need cross-encoder quality, but cannot afford joint scoring for every candidate. Caveat. The student can only learn what is present in its features and the candidate set. Next step, tune the number of trees and tree depth in LightGBM to trade latency for agreement with the teacher. If short, practical IR helps, subscribe and watch the rest of the IR videos.